Yeah, so today we'll talk about a recent work that I did jointly with Adam Boland, who was my PhD supervisor, and also with John Wright from Berkeley. And we call this paper the State Hidden Subgroup Problem and How to Efficiently Locate Unentanglement. So hopefully there'll be something in here for everyone. But at the core, it's the best place to start is with a motivating problem, which we'll call the hidden cut problem. So it's quite easy to state. Imagine that it's a state input problem. So you're given copies of an n-qubit state, a pure state psi. And I'm going to promise you that it's a product of two unentangled states. Let's say two n/2 qubit states, phi1 and phi2. However, you do not know which bipartition of the qubits support the two unentangled states, i.e. you don't know the cut that separates the state into the two unentangled factors. So just to be precise, by a cut, I mean a set bipartition of the qubits 1 through n into two disjoint subsets, right, that add up to all the qubits. And I'm going to need a technical condition here such that the cut is uniquely defined. So the second bullet point here adds this constraint that the factor states, phi1 and phi2, that make up the whole state, are at least epsilon far from any other product states. Right? So this makes sure that the cut is uniquely well defined, such that internally these two factor states are strongly entangled within themselves. Right? So there's only one kind of visible cut here. If you want to be more precise, right, we can just express this in terms of the trace distance or the cosine distance, because we're talking about pure states here. So the trace distance between phi1 and phi2 and any other n/2 qubit product state, regardless of where it's a product internally, has to be bigger than some cutoff epsilon. So the task is given t copies of such a state, psi, find the cut C efficiently. Right? So by this we mean using as few copies t, hopefully a polynomial number in the number of qubits, and also algorithmically efficiently, right? So not just query efficiently, but also using poly-n size circuits and poly-n time classical processing. So here's a cartoon kind of just to illustrate the fact that there's combinatorially many ways of partitioning a set, right? So there's an exponential number of possible bipartitions, which should kind of motivate the fact that this problem is not trivial. Right? Any questions about the motivating problem?
Yeah, so maybe to be nasty, so what's the motivation in terms of why it's interesting?
Okay, well, if the fundamental problem in itself is not motivating enough, we'll have some extra motivation that comes from pseudo-randomness in just a couple of slides. So thank you.
And maybe this epsilon, does it matter how far you want to be from the product state, or epsilon you choose? Is it something important?
The scaling will be.
It's a good question. So here, let's consider two variations of this. So this you can imagine kind of pushing different buttons in this formulation, right? So one modification, this first star here, is that why only two factors that make up the state? Why not m different factors, right? So kind of a state that is a combinatorial kind of product of m different factor states that will also work just as well. But for kind of pedagogical purposes, we'll keep in mind the two-factor scenario. But bear in mind that whatever we say today will also apply to the arbitrary many factor states. And kind of anticipating, I suppose, a version of what you asked might also kind of have to do with kind of like, what do I mean by this epsilon, right? So this is kind of the weakest kind of generic property testing condition that we can imagine. I can also imagine a much stronger promise, such that, for example, these two factor states are, in a sense, maximally entangled, or maybe it's even easier to analyze the case in which they're Haar random or IID Haar random. So you can imagine that now it's a much stronger promise and kind of a flat epsilon kind of entanglement entropy across the internal cuts. And indeed, in this case, we'll get some improvements. Not as much in terms of the number of queries, but everything has to do with the algorithm size and the circuit size and all that will be, in a sense, maximally optimal. So to answer your question, think of epsilon as a parameter. Things will depend on epsilon. But there are also, there's much more, many more parameters to play with in terms of the promise of entanglement, and that does matter. So what are the main results, right? Given all these variations of this problem, our main result is an efficient family of algorithms which achieve the goal of finding the hidden cut in an efficient way with poly-n time classical processing. And I'm going to structure the results in two columns. So theorem 1 will refer to the generic property testing scenario in which the two-factor states are epsilon phi from product for a constant epsilon. And theorem 2 will deal with the stronger promise of Haar random factor states. And we'll count the requirements along 3 categories. So the number of state copies required, the circuit depth, and the number of ancillary qubits. So in terms of the number of state copies, the query complexity, to find the cut, we'll only need order of n over epsilon squared copies. I'm also adding this kind of green colored detail here, which is kind of, you'll see that these algorithms will work by kind of producing samples. And it will work in a way that will kind of remind you of kind of various Fourier sampling algorithms. So while, let's say, the blue number here is the total number of state copies required, you only need coherent access to the green number, which is a factor of n smaller, to produce a sample, produce each sample. So per round, you only need order 1 over epsilon squared, which you could interpret as a constant. In total, you need n times that. The circuit depth is also, I guess, well behaved in the parameters, so order n squared plus something that's polylog n epsilon, and a similar number of ancillary qubits. There's some trade-off between these two quantities depending on kind of how carefully you want to, really resource optimize your algorithm. But I'm adding these, and I'm adding kind of these details here, just on the off chance that some of you may be interested in, I guess, thinking about implementations of this in more practical experiments, just because the requirements are so low. And they're particularly low when we look at the second theorem, which deals specifically with the case of Haar random factor states. So in that case, right, order n, number of state copies. And yes, you can interpret that as kind of this epsilon going to a fixed constant. Exactly 2 state copies are required to produce each round. And it's going to be order n rounds. And you should think of that as kind of a version of a kind of vanilla swap test in which you only need 2 state copies. And you'll see why in a second. Perhaps remarkably, there's a constant depth circuit required to implement each round of sampling with only order n ancillary qubits. So if you care about kind of practical implementations of things, then the second column should be quite appealing. Right, and just to repeat myself, the algorithm works by collecting, say, order n samples and at the end of the day solving a linear algebra problem over F2. So you will see that it will come out as a version of Simon's problem. Yes, please.
So I understand these parts of theorem 2 follow directly from theorem 1.
Not the algorithm is of the same family. I think the algorithm. Please.
Two Haar random states, I mean, they will be pretty far off. I mean, you can control how far they are from a product state, right? So yeah.
Right.
Haar random state, you can kind of control this epsilon, right?
Mm-hmm. You don't even need kind of this epsilon anymore. If I promise you that phi 1 and phi 2 are Haar random, IID Haar random states, then it's a much stronger promise. Like internally, they're much more entangled than kind of promising you a flat constant epsilon entanglement across internal cuts.
I think the question, I understand, was like technical. If the theorem 2 is a corollary of theorem 1, if you just put some epsilon taken from Haar measure and you are done.
No. So the answer is no. And there's some cute math behind that, depending on how interested you are. Like the algorithm is of the same family. Really, the work goes into analyzing the algorithm. I hope to touch on that. Yeah, it requires opening up the Haar toolkit a little bit more. Yes, yes. So for example, the fact that I don't need these kinds of circuit depths anymore is not trivial. Yeah. To give you kind of a taster in case we never get there. So this will be an application of Simon's problem, which will appear kind of magically, as they will be able to encode cuts as kind of secret strings and solve a hidden subgroup problem like Simon's-like problem. In the Haar random case, you actually will deal with a Simon's problem which does not produce uniform strings. And you'll need to kind of still show that that works, but it's an asymptotically different regime. So it will be a non-trivial modification of Simon's problem in theorem 2, while theorem 1 will be closer to the vanilla textbook Simon's problem. Just to anticipate kind of the conceptual differences between these two. So it's not just a corollary. Thank you. And yes, the algorithm works just as well for the many cut case, even though we'll keep in mind the two-factor state, i.e. one cut for the stock. And as a small detail, you don't even need to know how many factors there are, because you'll be able to infer that from the samples you produce. At some point, the matrices will not grow in rank anymore. Okay, so the rough plan for today, and I won't promise that I'll go into a lot of detail on all of these, but the rough plan is we'll take a look at what we know information theoretically about this problem. We'll talk about the motivation, which comes mainly from the world of pseudorandomness and pseudoentanglement. We'll remember how the hidden subgroup problem works, and we'll modify it to deal with state inputs, which is the scenario we're in. And we'll remind ourselves how Fourier sampling works to attack hidden subgroup problems. And we'll try to fit our problem into a state hidden subgroup problem framework that we will have just defined. We'll see that the more natural, non-abelian symmetric group approach will fail, but we can reduce that to, we can sparsify that to an abelian Z2 to the n approach. And that's exactly the Simon's problem structure will appear at the end. In other words, in our algorithm, we'll go from finding a hidden cut to a structure that deals more natively with Boolean subspaces, such that to each hidden cut will correspond a hidden Boolean subspace. We'll see that there's an approximate Simon's problem appearing that we'll be able to fine-tune. And there is a catch that there is a trick that I might mention briefly for how to reduce the number of state copies down to an optimal order n, as promised on the previous slide. For the special case of high random states, we'll need some version of a self-averaging result for all the internal purities of the high random state. So imagine looking at a combinatorial version of the page curve. I'll touch on that, hopefully. As I mentioned just before, the Simon's problem will need to be modified away from the clean textbook uniform case. And there's a very interesting open problem at the end, which I insist on presenting to you and advertising, which is modifying this problem slightly in as much allowing for some entropy across the hidden cut breaks down everything that we will have built up to this point. So all the algorithms so far will break dramatically if I introduce, let's say, a constant amount of entanglement across the hidden cut. And in particular, the Simon's problem becomes noisy in a way that reduces to a very famous crypto system, i.e. the learning parity with noise problem. If you come from error correction, it's the same problem as decoding random linear codes, right, which is widely assumed to be hard. So it's an open question of whether this version of the problem, of the hidden cut problem, as a quantum state problem, is indeed computationally hard, and whether it can be reduced to other interesting new native quantum cryptographic assumptions. So what we know, okay, let's go into the information theory very briefly. What we know about this problem. Well, this problem was not really dealt with directly, but there are traces of it in previous literature. In particular, everything has to do with, let's say, product testing and all the glorified versions of swap tests as used by, for example, Harrow and Montanaro in their celebrated proof that QMA2 is equal to QMAK, were extended by Harrow and Montanaro in 2017. And there appears a problem which we could think of as the decision version of the hidden cut problem. So in the hidden cut problem, what we'll talk about today, we care about finding exactly which cut separates the state. Harold and Montanaro study the problem of testing whether an input state is separable across any cut at all. So it's decision, is there a cut or not, regardless of where it is. And they have an upper bound, an information theoretic upper bound, so coming essentially from a trace distance calculation. That only order n over epsilon squared state copies are needed, information theoretically. Right. And a lower bound comes from quite recently. So last summer, Ashley Montanaro and his student Ben Jones published a note looking at the other side of this. And they show that there's a lower bound of n over log n state copies needed to test whether a separating cut exists. So we're dealing now information theoretically we're in the space between order n and order n over log n. Now that's really good for us, right? Because our algorithm exactly hits this upper bound optimally, right? And we know it's optimal within a log n to whatever the true optimum is. Now, just to be very clear here, these are information theoretic results, right? So if you want to think about these results as algorithms, they will be extremely inefficient algorithms. Like in other words, they're as efficient as kind of designing a binary measurement for each cut and then trying one cut at a time exhaustively, right? Via progressive gentle measurements. So these are by no means kind of recipes for efficient algorithms, but they give us kind of query complexity bounds. And this is good because this is kind of this means that our efficient hidden cut algorithms, right, which we'll develop in a second, are optimal in terms of number of copies, right, up to this possible factor of log n between the upper and lower bounds here, which is still open. And I should say at this point, right, that in a hidden cut problem, like I'm giving you a state, you know it's separable somewhere, but you don't know which bipartition separates it. Verifying the cut is efficient, right? And you don't need more than the vanilla swap test to do that, right? So once you know the cut, verification is simple by a standard swap test using only a constant number of state copies, right, within some high probability. And the swap test needs to be mentioned at this early stage because it's kind of the prototype for everything that we'll do further on. Like what we'll have later on as our algorithm will be kind of glorified version of swap tests, whether we modify exactly whether we lift this from a Z2 kind of qubit ancilla to a Z2 to the n, or whether we'll use repetitions of states, so we'll have kind of amplified swaps in this controlled operation. The swap test is still like the prototype for everything that's going to happen today.
So just to make sure that I don't miss, so the cut, so the subsets are always like ordered, yes? I mean, one set is on the left, the other is on the right, or there can be different places.
No, so there are.
It's a subset or a cut. Maybe this.
It's the same thing. So, right, going back to the definition of the problem, the two states are supported on two disjoint subsets.
Yeah,
right?
It's a subset. Okay.
So it can be, like this, or it can be like this. Yeah. Like the blue and the yellow represent kind of the two subsets, right? Or it can be like this, or.
I just thought that you maybe assume that it's left case only.
It's easier to draw the picture. Right, but there's no geometry to these states. There's no like 1D geometry or physical geometry to this.
Because then the problem would be much
really easy. Yeah. Really easy. Like it's just a polynomial number of cuts. You might as well just try them one at a time, right? So the whole idea is that even if I fix them to be, let's say, equal by partitions, right, and choose n over 2 is exponentially large, right? And that's why the problem is interesting. Okay, so a bit of motivation. Right. So there's been a lot of excitement around kind of importing the tools of pseudo-randomness from classical complexity into the quantum world. It's well known that hard random states, like genuine hard random states, require exponential depth preparation circuits. Right? You can use a counting argument to see that really. And in the seminal paper by Ji, Liu, and Song in 2018, first constructions of pseudo-random states were offered. Right? So the idea is to bypass this information theoretic obstacle of exponential depth preparation for Haar random states by introducing cryptographic assumptions. Right? So we'll spoof the Haar measure by defining these ensembles of states which are on one hand efficient to prepare, so they do not require very long circuits, but are nonetheless computationally indistinguishable from Haar random states. And those are these famous pseudo-random state ensembles. So in the past few years, there's been many constructions from standard cryptographic assumptions.
Sorry to
Please, yes.
Just most of the people probably are not that familiar with pseudo-random states. Do you mind just elaborating a bit, what you mean by computational indistinguishable?
Yes, certainly. So the best I can do is just to elaborate on precisely what's said here, right? If I wanted to give you, like the idea is to give you a state or state copies, right? And for you to tell me whether these come from the Haar measure or not, right? And ideally, these are states that I can prepare efficiently. So a perfect distinguisher, right? An information theoretic distinguisher would immediately observe the difference between a state which has been prepared in a short depth versus a Haar random state, which would take exponential depth to prepare. So we need something else. We cannot just rely on statistics and information theory, right? And that extra input is like a cryptographic assumption, right? So in the same way that I can, when you invoke a random number generator, right, and in programming, in classical programming, and you can kind of fix a random seed at the beginning, right? You're creating kind of a deterministic sequence of numbers, which are nonetheless indistinguishable computationally from genuine random draws from whatever, the Boolean cube or something like that, right? Even though they're deterministically obtained, right, and efficiently obtained. And we want the same kind of power over quantum objects. And the question is, can we do it from kind of known ways of spoofing kind of randomness classically? And the constructions of pseudo-random states achieve exactly that, right? So these are collections of states which are, in a sense, defined by, and I have here kind of a few examples, they're defined by, let's say, a sort of simple classical object. So in this, I won't go into too much detail, but some of these are defined by functions. And maybe focus on the second one here. Here's probably the simplest construction of a pseudo-random state is uniform superposition over all bit strings, and then flip the sign to +1 or -1 according to a random function. And that's exactly where the random/pseudo-random distinction appears, because instead of a genuine random function, of which there are 2 to the n, so that's quite a lot, I will replace that with known ways of kind of efficiently preparing like a pseudo-random function instead of a random function. So really, for all these constructions, I'm kind of using known classical ways of kind of spoofing genuine randomness with something more efficient, but somewhat computationally hidden. And then kind of lifting that into a state construction, and then ultimately showing that this state ensemble comes close in trace distance, if the randomness was real, to the Haar ensemble. It's okay if you didn't follow all of that, and logic is quite simple. I think what's worth remembering is that at some point I need I need to have like some sort of extra juice, like extra computational juice of some sort of classical distribution, which is very rich. Let's say all possible functions, let's say, or all subsets of a certain size, or something like that. And I have some way of spoofing that computationally. Right? So when I say that we build it from classical assumption, we mean that we use kind of a classical way of turning randomness into pseudo-randomness, and then having a workflow that takes one of these objects and preparing kind of a state from it.
So here you don't mean by computationally indistinguishable, you don't mean that it's not efficient to distinguish. Mm-hmm. It's kind of more fundamental indistinguishability. Not that it would take exponential time to distinguish, but that in principle you cannot distinguish it at all, yes?
No, I mean exactly that. I mean that these objects, so I think the easiest, okay, I think I'll have a slide with hopefully a somewhat clearer framework for this in a second. But
so I can just bump in. So maybe some cartoonic way to just rephrase what Turan just said would be that when you have many copies of those states, even quantum computer, but running for polynomial spherical depths, cannot distinguish from copies of a random state.
Yes.
So it's like a dual to this question of preparation, that you want efficient preparation so that it cannot be efficiently distinguished.
I want efficient preparation, which means that, let's say I fix the depth to be poly n for all these states. That's not enough to have a state ensemble that is as rich as the Haar ensemble. Yeah. So the trace distance between this ensemble, tth moment, and the Haar ensemble, tth moment, will be order 1. Like the trace distance is huge. So in principle, there are information theoretic distinguishers. So I need some extra reasoning to argue that, okay, there are distinguishers out there because the trace distance is huge. It's just that those distinguishers need superpolynomial depth to prepare. Right? And the way to engineer this kind of constraint is to introduce a cryptographic assumption, which is exactly about that. So when we're talking about trace distance to the Haar measure, right? In classical cryptography, you talk about exactly that, but you talk about total variation distance to, I don't know, uniform distribution over the Boolean cube or something like that. And it's the same phenomenon. That I could sample from a superpolynomial support, classically speaking, but you won't be able to distinguish from the uniform distribution genuinely with only polynomially many samples, right? And again, there needs to be an extra assumption. Like, this is more than physics, right? So a cartoon to maybe help our intuition a bit. Right? is kind of the classic page curve cartoon. So imagine here on the x-axis all the ways of cutting a state, and the size of, let's say, the size of cutting, I don't know, k out of n qubits out of an n qubit state, right? And on the y-axis, I'll plot the entanglement entropy across that cut. And think of this as a cartoon. It doesn't contain all the intuition you need, right? But usually in 1D systems, at least, we think of this page curve as going up or down. The Haar curve is up to kind of subdominant corrections, kind of linearly going up and down, right? And this is kind of what we mean by Haar random states being maximally entangled internally. Right? I should mention that some of these constructions we just looked at do achieve actually much more than just computationally spoofing the Haar measure, and also have this interesting phenomenon called pseudo-entanglement, which was coined in this paper by Aronson and collaborators a couple of years ago, which kind of showed that there's more space in the Haar measure, and you can hide extra physical properties in there. So in particular, some of these constructions here, and I will not go into too much detail, yes, achieve the pseudo-randomness property, i.e., given t copies of a state, it should be computationally hard, given a cryptographic assumption, to distinguish from the Haar measure. But at the same time, also hide, let's say, a large amount of entanglement. Like, we expect the Haar random state, right, to have order n entanglement here in the middle, like if I cut half of it. But a pseudo-entangled state actually will plateau entanglement somewhere above the log n threshold. Right? So nonetheless, a typical state from one of these ensembles is indistinguishable from Haar, and at the same time has a almost exponential amount of difference in entanglement from what we would expect a Haar random state to have. So you can interpret this as kind of entanglement here in the middle is not necessarily feelable within quite a huge range, right? Now, why do I need this cutoff of entanglement to be right above log n, like little omega of log n? Right? It's because there is sort of a cloud line here at log n because of the swap test that we just discussed. Right? So if I have a cut, right? If I have a cut that has like detectably low entanglement, i.e., below log n entanglement, I should be able to test that, right? If I know where the cut is, I can run swap tests. It will pass with probability 50% plus something that's 1 over polynomial. With polynomially many samples, I can kind of feel an entanglement that's below. And so pseudo-entanglement is a cool phenomenon, right? But I think there's two interpretations to it. Like, I think it was also meant to, in a sense, scare physicists, whereas, and kind of show them that something that we thought of as being extremely physical, right, might actually be computationally indetectable through quite a big range. On the other hand, I think if you ask like a theoretical computer scientist, they might tell you that, oh, okay, above log n entanglement here, I guess it's a cool geometric property, but the rank of these states, the Schmidt rank of these states in this regime above the cloud line is still super polynomial. So if you had an algorithm, it will need to run in polynomial time, but you're giving a super polynomial input. So of course, like, I can still hide everything above the cloud line. So a hidden cut state aims to be like a dramatic addition to this, right? Because a hidden cut state will actually pass below the cloud line here in the middle, where it would have exactly zero entanglement, right? And so a motivating question to study hidden cuts, right, is what can be hidden below the swap test cloud line? So, and I think hopefully this schematic here might answer your curiosity. So in a standard PRS constructions of the kind that I've listed before, the pseudo aspect still comes from classical cryptography. So in other words, usually people, like, we calculate, let's say, this type of proximity. So let's say we have a state ensemble parameterized by some f object. Think of it as a function or some rich classical object. And if I treat that function as a generally random classical object, then I can do a physicsy calculation and show that the teeth moment of the Haar measure is close to the teeth moment of the ensemble when that object is generally random, right? And then I pass to the pseudo world in which I replace that classical object with a pseudo-random distribution over these objects, and I sparsify it like by a lot, like I de-randomize it essentially. And then, whereas here I had genuine trace distance proximity, here I only have computational indistinguishability now. The trace distance would be huge. So this workflow here is what I call kind of a classical phenomenon of pseudo-randomness, right? And a motivating question for the hidden cut problem is to try to obtain native quantum ways of similar phenomena, right? So are there new natively quantum ways of achieving the same effect, right? So for example, here's a very clean question along these lines. Can we have a recursive PRS construction such as the following, right? If I have a pseudorandom state on n over 2 qubits, well, two of them, let's say, two pseudorandom states on n over 2 qubits, right? Just put them together and then scramble the qubits classically, right? Permute the qubits, i.e. hide the cut, right? Is this a recursive PRS construction on n qubits now? Now, because as we'll see, there's an algorithm to solve this problem, right? This is a version of the hidden cut problem. This specific construction is forbidden, but later we'll see a modification which is still open by adding kind of more rank, and not that much, just a constant amount of rank across the cut. So,
just
yes.
to understand, so when you started studying this problem, you actually perhaps wanted to show that this ensemble of states.
Yes. Yeah. So I think a lot of people are surprised that this is possible. Okay. Yeah. Yeah.
But then your algorithm, which is about this thing in the middle, sort of prevents.
Exactly. Okay. So the fact that, as we'll see, there is an algorithm, right, forbids this recursive PRS construction, right? Because if I give you the state and copies of the state here on the right, I can distinguish from something that's genuinely hard because I can find the cut and test for it. Yeah. Yes, please.
Is there intrinsically any reason why would you suspect that such a recursive construction is possible in the first place? Or it just like sounds like a simple, plausible construction?
I would say that there's a reason why this, you can think of intuitive reasons why this very simple version of it with exactly zero entropy in the middle should probably be forbidden, because you can imagine kind of pressing this down and getting kind of a very simple state up to a point, right? Why, let's say, extensions of it that allows for some entanglement across the cut, why that would work? I can't think of necessarily okay. Maybe this is not satisfying, but I think we do have recursive constructions in the classical world that work quite well. And I think there's been a bit of a problem in. So classically, you can have you can just generate randomness and stretch it kind of to polynomial extents, right? Something that you cannot do with random states. So I think, understanding to what extent you can build these recursive constructions is part of kind of understanding this terrain between classical and quantum cryptography, I think, yeah. And something that's amenable with, I guess, just geometric tools, Okay, I know this is very high level, and I'm happy to answer a lot of questions now or offline, but any pressing questions on kind of this motivation? Because we won't see this logic until the end of the talk again. All right. So, let's talk just a bit about kind of design principles. So, any hidden cut algorithm. So now we're moving back to the hidden cut world, right? Any hidden cut algorithm will have to perform entangled measurements on, let's say, the global state, right, made of T copies of the input state, and maybe I'll represent it as this kind of grid of qubits where each row, right, is an input state, and I've kind of conveniently laid out the cut for you kind of as the first half and the second half of the qubits. Right? So a basic principle of algorithm design is take advantage of the symmetries of the global state. So any operation, right, any unitary, let's say W, which acts on this global state and preserves it, right? And remember that we make no assumptions really about the internal structure of these factor states, phi1 and phi2. So all symmetries really must act across, i.e. vertically in this diagram, right? Not along the state copies, not along the rows, right? So really here, I seem to not have much more to work with than the natural permutational symmetries of this problem, right? So again, the rows count the T copies, and the columns count the n qubits, right? And if I'm giving you a state of this kind, in which there are T copies of the input state, right? Any permutation that exchanges half the state, right, exchanges one segment of the cut, right, across the T copies, will be a permutation that preserves the global state. Right? So here, if I apply the same column permutation to the columns making up the first section of the cut, right, I exchange these blue segments exactly between the T rows, and I get back the exact same original state. Right? And similarly for the other half. So applying the same permutation across the copies on the qubits inside each side of the cut preserves the global state. So you're starting to see this intuition that to each hidden cut corresponds a hidden subgroup. So in this case, as kind of depicted here, it's ST, like the symmetric group on T elements, ST cross ST, right? Because there's one copy of ST for each side of the cut. Inside maybe like a parent group that contains all possible column-wise permutations, right? So ST cross ST cross ST n times. So this is already kind of has a very strong hidden subgroup problem flavor, right? Except I have a state input and not kind of a vanilla hidden subgroup problem, kind of oracle input. Is this picture clear? Because we'll see versions of it again and again. Okay. So I'll glance through this really quickly. If you've seen this before, great. If not, don't worry too much about it. Right. Again, we're starting to see kind of flavors of hidden subgroup problems, except that there's one major difference, right? In the hidden subgroup problem, as defined in the textbook, the input is a function and not a state, right? So if you might remember from kind of introduction to quantum computing, that the hidden subgroup problem refers to kind of access to a function defined on the group, such that the function takes the same value on items of the group which are part of the same coset, where the coset is defined by an unknown subgroup H inside the parent group G. Right? And the task is given oracle access to F, determine the subgroup H. Now this seems really abstract, but it captures like an enormous amount of problems, right? So in particular, a billion hidden subgroup problems, right, capture many famous cases of quantum algorithmic speedups. So all the greatest hits, right? Period finding, Simon's problem, Bernstein-Vazirani, a billion discrete logarithm, and you name it. At the same time, right, the non-abelian versions with various discrete groups capture many key problems that are still assumed to be hard, right? So if you could solve the HSP over the symmetric group, right, with a quantum algorithm, then you would have a quantum algorithm for like famous hard problems like graph isomorphism, right? Or if you could solve HSP over dihedral group, then you would pretty much break the most popular candidates for lattice-based post-quantum cryptography, in particular the learning with errors problem. So there's still no known efficient algorithms, and we trust the hardness enough to kind of build crypto systems on top of these types of problems. So this is kind of the canonical example of an information computation gap, right, in quantum complexity. Because HSP is information theoretically easy. You only need a small number of queries, as shown like in this kind of famous paper by Ettinger, Hoyer, and Nil from back in the day, 20 years ago. So to go from a problem that has a function as an input, right, to a problem like ours, which has a state as an input, we will need to adjust this a little bit, and we'll define a state hidden subgroup problem, which hopefully will be of independent interest, and actually might be. I'd like to actually advertise if you can find interesting problems that can fit into this framework. So instead of having a function oracle as an input, I have a state as an input, right? So my input is copies of an input state psi, such that there's a representation acting on kind of this ambient Hilbert space that in which the state resides, such that there's a hidden subgroup that under this representation preserves the state. Right, so R of H on psi is exactly psi for all subgroup elements. And at the same time, the state is displaced by the action of non-subgroup elements. And here we have kind of an important difference, right? Because if I apply a group element on the state, it moves away from the state with some kind of non-orthogonality parameter epsilon, right? And the task, again, is to determine the hidden subgroup H. Don't worry too much about this. I think what I want to convince you is that this is actually not a dramatic difference from kind of what we know about the hidden subgroup problem. Right? In particular, if I had perfect orthogonality here, in other words, any non-subgroup operation would take my input state to something that's orthogonal, I would get something that looks very much like the standard hidden subgroup problem. So really, you should think of the state hidden subgroup problem as generalizing HSP, the hidden subgroup problem in the vanilla sense, beyond the regular representation of the group. The reason for that is that the standard approach to HSP already involves kind of transforming it into a state problem and then dealing with the states. So you build the so-called coset states in a very simple way. I won't go into the details here, but the idea is that you natively build kind of states which have perfect orthogonality. And I'm interested in more
flexibility. You have like channel discrimination versus state discrimination, so you can play with these pieces.
Right, for sure. And we can imagine a few versions of these problems in which maybe some aspects of representation are not known and so forth, right? Yeah. But we'll be interested in just having kind of, yeah, in a minimal extension of this in which we have, let's say, orthogonality allowance that's not perfect. Yeah. And let's say a representation which might be somewhat arbitrary. Yeah. Yes. So given an efficient circuit for the quantum group Fourier transform over the group, and again, I know that I'm kind of throwing at you this group theoretic and representation theoretic language, but for our purposes, ultimately, it will not be very helpful. So if you like that sort of stuff, like I'm happy to chat. Don't be intimidated by, let's say, the non-abelian kind of representation theoretic language. Ultimately, the algorithm of interest for this problem will be fully abelian. Now, there are interesting open problems, perhaps, trying to kind of deal with the non-abelian cases for these problems later on, and I'm happy to discuss about that. But the idea is that we can still import the tools of Fourier sampling that are known to work for like a variety of standard HSP problems, right? So on the left here in HSP, here's a well-known structure for how to obtain Fourier samples from the action of let's say a combined action of the Fourier transform over the group, and then the oracle application of the function, right? In the function that is kind of the object of standard HSP, whereas in the state HSP framework, instead of I start from the input state psi here, and I can apply just the same as on the left. I apply the Fourier transform over the group and the control representation that makes the object of the group action. In both cases, I obtain probability distributions over some objects, i.e., the irreps, the irreducible representations of the group. And I just want to emphasize that the difference is actually kind of minimal. So here's the probability distribution on the left in terms of characters and whatever, but all you need to kind of notice is that there are these kind of inner products that now control the difference between the left, i.e. perfect orthogonality case, standard HSP, and the right, which has kind of a bit more flexibility. And again, the goal, this is a framework for kind of producing algorithms that are known to work in the abelian case, and in the non-abelian case, of course, they only go to some extent in some simpler cases, but they fail in various ways to solve the problems that are assumed to be hard. And an important observation is that when we have enough orthogonality and access to poly n state copies, I can amplify these things. And I can kind of amplify the orthogonality. Like literally, wherever I have these inner products, right, that make the object of the difference between these two cases, having t copies of everything puts a power of t on the inner products. All the inner products which are less than 1 get suppressed, right? All the inner products that are 1 remain. So in other words, like the takeaway here is that if I do have access to poly n state copies and enough orthogonality to begin with, I can reduce state HSP to the standard HSP with the same specs from the point of view of a Fourier sampling routine, right? So with t equals poly n state copies, I can take the probability distribution of state HSP and bring it down to the probability of the vanilla HSP with the same subgroup group specifications. And yes, there's an open problem, as I promised. Are there meaningful instances, i.e. it will require probably clever group theoretic constructions for which this reduction is not available? But I will say that, this assumption that you always have state copies available might not be exactly as realistic and there are interesting applications where you don't have that. Right? I think of quantum money and stuff like that. I'll briefly mention the fact that sort of the most generic set of symmetries for the hidden cut problem that would fit it into a state HSP framework, i.e. the full permutational symmetries like ST cross ST, right, where I have one instance of ST for each side of the cut, actually fails pretty dramatically from the point of view of Fourier sampling, right? So yes, if my goal now is to kind of use that observation from before of trying to bring the state HSP to HSP to something a bit more familiar by amplification via more copies, I need to find kind of the right group action to impose on my state problem to make it a well-defined state HSP problem. And the most natural one, this is the same graph from before, is the full permutational symmetries. And yes, this defines a correct state HSP problem such that to each cut in the hidden cut problem corresponds a hidden subgroup inside this parent, st to the n non-abelian group. And we can apply Fourier sampling because we do have efficient quantum circuits for the Fourier transform over the symmetric group, right, since the 90s. So identifying the subgroup from this sort of most generic type of group action actually fails pretty dramatically for the same reason that Fourier sampling fails to solve the generic HSP over Sn. And I'll refer you to these kind of tour de force papers from Chris Moore and collaborators from 2005. The idea is that, yes, like more copies, right? More copies meaning the T gets larger. Indeed, as mentioned before, brings my state problem to HSP, to the kind of generic HSP. But at the same time, T is also a parameter which makes the group theoretic problem much, much harder. So as I increase the number of copies T, I also am chasing after a much harder target, and the second effect wins over. And the solution to it is really to keep things as simple as possible and to keep things abelian. So this is going to be a framework that will work for us. I'm going to express the hidden cut problem as an abelian state HSP over Z2 to the n. So yes, I'll still work with these permutations, but I will restrict them to only to an abelian subset. Right? So here's a simple action of G is Z2 to the n on my input state. Right? And my input state is made of T copies. Let's take T to be even. Of the input state. So each row here again is the input state made of two unentangled factor states, and there's T of them, in this case 4. Here's a simple group action of Z2 to the n, right? So here's a bit string of n qubits of size n. The locations where I have ones, right? On those columns, I apply I exchange that qubit across neighboring copies, right? So I think the picture speaks better than I can. So wherever I have a 1 here, let's say I have a 1 here on the second position, it means that I exchange the qubit, the first qubit of the second column with the second qubit of the second column, the third qubit of the second column with the fourth qubit of the second column, as depicted by these arrows. And I do that for, in a commuting fashion for every column, right, where I have ones here. So I obtain a state which is now, of course, not the same as the original state, right? But this defines a well-defined abelian group action of Z2 to the n on, any T cross n qubit state, really. And the same type of logic of the hidden subgroup problem applies here, right? So in particular, if I flip simultaneously, if I have a bit string which is all ones on one side of the cut, this means that I exchange the full kind of factor state across neighboring copies, and I retain the exact original state, right? And similarly for the other side of the cut, exact mirror opposite, right, as depicted in these two plots. So in other words, to a cut C bar, meaning a bipartition of n qubits into two subsets, this determines a hidden symmetry subgroup, right, HC, of size 4, like it's just Z2 cross Z2, which means that, well, it contains the 0, i.e. trivial action. It contains the all ones, meaning I just flip everything, and I exchange. I exchange the full state across neighboring copies, or again, as depicted here, I exchange one half of the state or the other half of the state exactly in the location of the cut, and this preserves the input global state. I'll say that I talk about kind of this action in the abstract, but if I come in, let's say, with an ancillary and qubit system, this group action is trivial to implement by a sequence of controlled swaps, right? And the Fourier transform over Z2 to the n is just Hadamard gates. So all the apparatus of Fourier sampling is trivial to implement in this case. So here's really a depiction of how this works, like almost literally. If I imagine kind of each of these rows containing a copy of psi, and these are the n qubits that encode the Z2 to the n action, it's really just parallel amplified swap tests. And there's one swap test, well, amplified, I guess, T over 2 times, perhaps, if there's T copies here, for each qubit of the state. The outcome, right, of a Fourier sampling experiment like this is a distribution over bit strings, right? And the key observation is that, once again, with more copies, I can amplify away all the inner products between kind of non-preserving state operations, i.e. all the inner products which are less than 1, I can suppress. Right? So when the smoke clears in this analysis, I'll get a probability distribution which looks quite interesting. Right? The idea is that if the key objects, right, in this analysis will be kind of Fourier transform of these types of inner products, where R of x, imagine it as a group action. And this turns out to be just a power of the purity of the state according to a particular type, a particular internal cut of the state. So a nice observation here is that this deals natively with kind of all possible ways of cutting a state and defining a purity for each possible cut of a state. Something that appears, so let me restate that. Let me restate that sort of as in a language that will appear kind of more familiar to, more familiar with respect to, let's say, hidden subgroup problems, with respect to Boolean functions. Because ultimately what I have here as the probability distribution is a Fourier transform of all possible internal purities. So something that appears of this analysis, right, is a Boolean function defined by a state such that for every bit string, for every n bit string x, right, every n bit string x defines a cut of a state. Right? So if you have a string of zeros and ones, the locations where you have ones, you trace those out. So this is a natural kind of Boolean function defined on a state. The probability distribution that I get out of one of these experiments is precisely a Fourier transform over all possible internal purities of the state. In some condensed matter theory literature, some of these objects are called entanglement features, meaning kind of this combinatorial view of all possible kind of internal purities of a state at once. So it's quite of an interesting way of obtaining kind of a Fourier sampling natively out of all internal purities of the state. So the idea is that the purity or any entanglement measure, right, is invariant when if I trace out a subsystem and I get an entanglement there, it's the same as tracing out the complement of the subsystem, right? And that's the source of the symmetries here. So, in other words, this function that I'm kind of taking a Fourier transform of to obtain my outcomes has kind of natural symmetries. And not only does it have this global symmetry of kind of exchanging a system for its complement, but it also has the same symmetry at the level of each factor state, right? Because it's made of two kind of unentangled factor states. The catch here is that whereas this would remind you of Simon's problem in the following way, right? In Simon's problem, you had access to a function f, which had the same value when you shifted the argument x by a secret string s, right? In our hidden cut problem, you get exactly the same type of structure where you deal with, instead of a function, now I have kind of these internal purities of the state. The purity remains the same if I shift the cut of the state by an element of this hidden subgroup, i.e. By the complement across the cut. So whereas before, in the Simon's problem, I can apply Fourier sampling and I obtain samples which are orthogonal to, let's say, I obtain sample from the Boolean cube orthogonal to the secret string. In the same way here, in the large T limit, I will obtain samples from the Boolean cube, which are orthogonal to all the strings in the hidden subgroup. So the idea here is that I get something that's really reminiscent of Simon's problem, such that for every hidden cut, there exists a hidden subspace, right, defined by all the elements in the symmetry group. Because shifting any internal purity, like any way of partitioning the input state, shifting it by one of these elements leaves the purity unchanged. And that's, in a sense, a hidden symmetry of the purity function. I will spare you the details of the analysis of exactly why, exactly how large T needs to be to obtain this limit, right? But the idea, it shouldn't be too surprising that, at the end of the day, when you have these kinds of sums and you amplify, let's say here with the number of copies, really only the 4 points which have purity 1 survive, and all the others are suppressed, right? And what points have purity 1 of a hidden cut state? Well, the trivial, i.e. no cut, or the full cut of the system, or exactly the correct cut. And essentially, if I have only the four terms that survive from the sum, all the others being suppressed by being less than 1, right, with a high power of t, then you get exactly this type of uniform distribution over a subspace. Now, this is a subspace of dimension n minus 2 in this case, because I have, right, 2, it's z2 to the 2 that forms the hidden subgroup. If I had k different factor states, it would be, n minus k dimensional, and the same logic would apply. So the idea is that in the large T limit, I get these kind of very clean uniform distributions over a hidden subspace. This is exactly what happens in Simon's problem with some minor differences in terms of the dimension, but the idea remains the same. We collect order n samples to have a full basis for the subspace. So we do this kind of basis coupon collection. And at the end, we can just find the secret, just like in Simon's problem, by solving a simple linear system over Z2.
Like, if you can finish in 5
Yeah, exactly. Yeah. Sorry, Martin?
5.
We have a question. 5 minutes. Got it.
Okay. If you go back one slide, if we think about applying this procedure to a hard random state, kind of what determines that on the how many samples we need are basically those how small the non-trivial purities are, right? And this is kind of like we can, I mean, for a hard random state, we can estimate this, but it looks like it's a kind of we are using something much bigger, right? It's kind of like more like a design property of sorts, right?
So you're curious about the hard random case here, right?
Yes, I'm saying that it seems to me, just looking at this, that we don't really, at this level, we don't kind of use the full power of the randomness, or I'm mistaken?
Right, exactly. Like the so
because we only need the purities, non-equal to purities which are not equal to 1 to decay sufficiently fast. And I guess this kind of like the purities are kind of like a two more second order properties, right?
yes.
If I replace the
Yes.
random state by a two design, would like the conclusion be the same, or there are some subtleties?
So let me say that, for example, if all you have is a weaker promise, right? Oh, all I know is that I have some sort of epsilon cutoff for the internal entanglement across the factor states, right? So something much weaker than hard randomness. Then that gives me kind of a bound away from 1 for all these purities which are not 1, right? I know that all the other like I have these 4 purities which are 1 that have to do with the trivial cuts and the right cut. And then all the other purities are, I don't know, 1 minus epsilon squared or something like that. And that gives me control over the sum, right? And gives me control over how much I can, how much t I need to suppress the other terms. And in the hard random case, I'll skip over the adaptive modification, but just hopefully, this is a slide on hard randomness, right? This is literally what's needed for the hard random case. Like no more amplification needed. And the reason for that, I think, has to do with, I'm wondering if you, actually, I think you need a 4 design. I think a 4 design might be enough for you. The reason for that is that in the hard random case, you actually do not need to approach the Simon's HSP distribution anymore. That actually those sums that I expressed, the Fourier sums that I expressed there in terms of the purities of hard random state already self-average very cleanly. And we have that kind of a self-averaging argument in the paper. So in that case, for example, they average to, like this is the type of distribution you would get. Instead of giving you kind of uniform samples from within the subspace, you're getting samples that are skewed towards shorter weight strings with something like a binomial distribution here. Like it's equivalent to sampling strings which are Bernoulli 1/4, kind of IID, and then kind of rejecting until the sample is in the cut subspace, as opposed to Bernoulli 1/2, i.e. uniform. So it's actually a skewed distribution, and there's a bit of work needed to be done, kind of to show that you get kind of full rank matrices with constant probability and the linear algebra, which when you have symmetry, you can kind of deal with it very cleanly. When you don't, you need to work a bit. But we can take it offline. Okay, so this is the last slide, right? This is the problem that I promised. So we saw how we can find the cut. We saw that kind of Simon's problem appears in this interesting way. And we saw that it has to do with kind of exact symmetries that are there, because I can imagine exchanging the subfactors across the copies is an exact symmetry of the global state, right? Now imagine this natural modification of the problem where I now allow for some rank across the cut. So rank 1 is what we've seen so far. We have an algorithm for it. It's optimal. And it works by this kind of abelian hidden symmetry argument. In this version with a constant rank, right, across the cut, so now imagine that I don't just have alpha across beta across the cut, I have like 2 pairs of alpha 1 cross beta 1 plus alpha 2 cross beta 2 across the same cut in superposition, right? So now I don't have, the symmetry is broken now, right? Like ever so slightly, because information theoretically nothing changes. The cut is still verifiable with a constant number of copies by a swap test and so forth, right? The algorithm now fails to find a hidden cut in a dramatic way. And the reason is computational or cryptographic, if you will, right? In other words, the samples, before the sample, you get these samples which are always within the cut subspace and nothing from outside. When you have this broken symmetry now, you will have a non-zero probability of having samples which are from outside the correct cut subspace. So in other words, when you solve the linear system at the end, it's like solving a linear system over Z2 where you corrupt a certain number of equations, like a certain fraction of equations are corrupted. Right? And this is the famous learning parity with noise problem, right? Which is widely assumed to be computationally hard and quantum secure. It's equivalent to the problem of solving, of decoding random linear codes, right? So the open problem right now is fascinating. Is this version of the hidden cut problem computationally hard, right? Information theoretically nothing changes. Our algorithm, which feels so simple, fails dramatically. The question is, well, is there a different algorithm to find the cut in this scenario? If there is, what would it look like? Because clearly it needs to follow a very different pattern than what we've seen so far. If there isn't, well, is this a native cryptographic assumption that is new and natively quantum? Can it be reduced to other interesting kind of cryptographic assumptions, right? So here, for example, what I've mentioned, this reduction to LPN is kind of in a boring direction, right? Like if you can solve LPN, like good luck with that, you can also find the hidden cut. Ideally, we would also have a reduction that goes the other way. Like starting from some sort of crypto system like this, can I prepare a state which kind of has a hidden cut somewhere of some sort of shallow rank, or maybe even polynomial rank, such that finding the cut is equivalent to kind of breaking the original crypto system. And that would kind of have a reduction both ways, and we would have learned something new about the computational hardness of entanglement. So this is the open problem that I wanted to advertise. This is the last slide, so thank you so much for your patience, and happy to hear questions.
Thank you, Tudor, for a nice talk. We are a bit over time, but maybe we have time for 1 or 2 quick questions.
So maybe the last slide, is it related to non-abelian case of Tudor? Because you had this nice distinction of abelian, non-abelian, everything hard becomes non-abelian. Here, adding noise, it's nothing to do with making the group non-abelian.
Not at all, no.
Noisy version.
And I wouldn't even call it noise. Like this is, it's a valid input state with a shallow cut, right? The cut is just not zero entropy anymore.
Okay. Is there a reinterpretation?
So definitely not in the framework we've seen so far, because now the symmetry is not perfect anymore. Like even if there is, now the clouds are not disconnected anymore in those plots. Like now I have a bit of entanglement in the middle, right? And I don't have perfect symmetries anymore. Yeah. So it's not clear how to fit the hidden subgroup framework to this case. Yeah.
Any other question or comment?
I have a general one. So this is more like your opinion. So you kind of use this word, how measure is physics. No? And I always struggled when I talk to experimentalists to convince them that this actually is. No? Because your whole work is how we can get to kind of how measure type of properties with pseudorandoms and so on. But actually to recreate a random state, you actually need to do all your machinery of quantum circuits and so on. So what's your take on that when you use the phrase, actually if you go to someone, experimentalist, tell him create me a high random state, he will say it's actually hard. No? So if I was a kind of devil's advocate, I would say actually the problem you start from is already hard to simulate in the lab, so what would be your kind of take on that?
Well, I think like, we're actually learning that spoofing the harm measure is, in a sense, easier than we thought, right? Whether we're talking about pseudorandom states. So these standard constructions of PRS, like, okay, this is exotic, but think about, the PRS constructions of the past, 6 years. Like, at the end of the day, we're able to spoof the harm measure over states starting from, let's say, a very known mechanism of pseudo-randomness.
Okay, are you spoofing the right thing? I mean, is the harm measure actually the right thing? Why should we care? Sorry for that. Okay, it's interesting.
It's interesting, and it's interesting. It's the most maximally complex. I feel like if you can spoof the harm measure, you can spoof anything. Maybe. It sounds like maybe you have your own opinion.
No, I'm actually trying to.
Okay.
So maybe just. So for mixed states, you can do something, or there's not interesting, or it's not possible to do anything. Like, I mean, at least distinguishing correlation versus no correlation. I'm not talking about entanglement, just correlation versus no correlation. Could it work similarly?
So I don't think it would work very well. Like, in a mixed state, in a sense, it's almost like it's like having it's like you don't have genuine copies of the pure. It's like having pure states that come from different distributions, right? You break these symmetries immediately, even in the unentangled case. So maybe it would work if you. So all of this, I guess you could imagine algorithms that would maybe even go even faster if you have extra information about the states, right? Like, if you know if the states come from a very particular ensemble, maybe they're stabilizer states or something, and you have kind of other symmetries you can add to the mix that work, across the rows of the diagram, not just across the columns. Maybe in that case, and that could be also interesting for applications. But it seems like the mixed states are even more fatal than this for like a very fundamental reason.
Okay, I dare to have one quick technical question. So Rafał asked about channel discrimination when you mentioned hidden subgroup problem, because people typically do try to solve this problem via this applying this representation to the state, to some states in regular representation. But are there other approaches? Did they actually use the machinery that was developed in the last years that is about distinguishing channels as opposed to states only? Because you have more ways of distinguishing channels than just applying a channel to a state and then doing something with it.
I'm not aware of that. I don't know of ways of unless you're able to turn. So I agree that there's a bit of flexibility between thinking of HSP as either a function state input or a state input problem, and that's kind of two sides of the same coin, maybe. And I think because we know of the reduction, like, those are kind of the cases that interest us the most, right? I don't know of clean ways of turning these state problems into channel problems as easily, right? So maybe you have something specific in mind, but it seems like I don't know ways of turning these state problems, for example, into channel problems with kind of low overhead or efficiently.
Right. So there is perhaps like a chance that by exploring channel distinguishability.
So I would say that maybe like one answer to this question would be, because now we're kind of relaxing things away from the regular representation. If we think of vanilla HSP as regular representation, now let's say we're opening the box of all possible representations maybe. I would imagine that there is a family of state HSP problems in which, let's say, the unknown is not as much a subgroup, but maybe some property of the representation itself. And then it becomes something that seems to have the flavor of channel discrimination. So kind of using kind of representation properties, the EREP structure, multiplicities, some versions thereof. That would be an interesting kind of variation on state HSP, which we haven't touched on at all, right? But I would imagine that this requires some clever group theoretic constructions. Like, I don't think you can do this with these kind of off-the-shelf groups. Like dihedral is too simple in a sense in terms of E-reps. Symmetric is too complicated in terms of E-reps. Like, you need crazy algebraic combinatorics to deal with. So it seems like the answer might lie in kind of finding some elegant kind of polycyclic groups or something that for which kind of the E-reps are just interesting enough, but also analytically tractable. Yeah.
Okay. Thanks then. Okay, let's thank the speaker again.
Thank you.